So, onto our topic, spectroscopy, multi-object spectroscopy. So we've had a very good introduction from Andy, who's not in the audience at the moment, but thanks Andy, in the ether. And so I'm just going to sort of expand on the topic by, I guess he covered a little bit about multi-object spectroscopy already, but it's a multitasking method for a spectroscopy. So this is why I have our little friendly octopus here, who's got many little arms, and so she's using her little arms to do different things at the same time. And so that's kind of what MOS does. I'm going to say MOS for short. I just mean multi-object spectroscopy. Otherwise, I'll be stumbling on my words the whole talk. So here are 3 examples of MOSes, and this is a very narcissistic talk. I said the same thing last time I gave it. I put pictures of me all over it. But anyways, this is here me with Force 2 on the VLT, and here I am with DMOS. So we saw pictures of DMOS already before. So this is DMOS again. This is Lee Sittler, who gave a talk yesterday. And then this is GMOS without me. Okay, so basically we saw from Andy they're quite big beasts, they're big objects. This one is basically this whole entire thing is the instrument, and it moves with the telescope. So in this talk I'm going to cover why we do multi-object spectroscopy, say a bit about, like, there are different types of multi-object spectrographs, so I'm going to say a bit about both of them, slit masks and then slits or fibers, and then cover a little bit about the future, so things that are planned of the telescopes and new and improved multi-object spectrographs to come. Why do we do MOS? So here's an example of a galaxy, and so if you had just a single object like that, you'd be quite happy to just put a slit on it, wherever you prefer to get a spectrum from, and then just get a spectrum of that area. Now, if we just look at that image for a little bit, I'm just going to point out a few things that are on there. Can everybody see the vertical lines going through like that? Anybody got any idea what that is? Skylines. So I can see some people here do spectroscopy. And then what's this here? What are these lines that are not vertical? Correct. The rotation. Yeah, okay, so these are the emission lines of the galaxies, and the reason why they're not vertical is because this galaxy is rotating. So the emission lines are moving. Okay. So, but what if I have something like this? So I'm looking at, say, an open cluster, and I've got multiple stars to look at. Do I really want to go and then select? Sorry, and this is a cluster of galaxies. So do I really want to go and then put a slit on whatever, like a range of random stars? I mean, the only really stars that I could pick in this would be 2 stars, and then hope for that the other ones are interesting if you want. The same here for the cluster of galaxies. So what you really want is to be able to put bits of your slit. If you could split that slit and then put it up and down in little chunks to actually image, or not image, but get a spectrum of very specific targets, that's really what you would want. That would improve your returns. And that's essentially what we do. And especially if you want to get like a whole ton of redshifts to make, say, a redshift survey, and then you're not going to go and then put a long slit on every single one of these things, you can get a map like that. You really have to have a multi-object spectrograph. You can, if you want, get the spectrum, so you put the grading in, no slits, and what you get is something like that. So you get streaks from each of the objects on the field. You're going to get a spectrum, but then the spectra overlap. That's not great either. So that's kind of why you prefer to have just the light from just the sources that you want to measure. Because after that, that's a data reduction nightmare. Okay, they've done pretty well, okay, but I think this looks horrendous to me. Okay, I don't want to have to deal with this kind of data. So what we do with multi-object spectroscopy is that we either use multiple slits, like I was describing before, or fibers, or optical fibers, to actually align exactly on top of our the object that we're interested in, and then get just the spectra of just these objects. So this is an example if you had multiple slits. And then once you get through your spectrograph, this is the kind of spectra that you would get. So you can see again, okay, so we see the same spectrum throughout I've reused, but you can see the rotation of the galaxy with the different emission lines. That's the spectrum from this slit, and then each slit would have a different spectrum. And here are sort of like stellar examples of the same thing. And one thing that I'll point out is that what you want to be careful. I'm going to say a little bit of like cautionary things depending on how you design your observations if you're doing multi-object spectroscopy. But something that's really important, and that not all the multi-object spectrograph slit mask software check is for overlapping slits. But even the ones that do check, they sometimes fail, okay? And then sometimes there is a way that the user can mess it up and then actually have overlapping slits. And so can you imagine if you have overlapping slits here, you're going to end up with a spectrum that's a mix of both in the middle. Okay, so you have to always double check that your slits are not overlapping. So this is one of my favorite data sets that I've had to deal with. This is just an exposure from DEIMOS, so just a raw exposure. And so in here there are planetary nebulae, there are stars, and there are globular clusters and H2 regions. Okay, so if you look very, very carefully, you can see some emission lines. There's an awful lot of skylines because it's in the sort of near infrared-ish range. So there's a lot more sky. You can see skylines than the previous slide I was showing. And then in here in the middle, there's a lot of light. That's because it's actually overlapping with the background galaxy. So these are just objects that are around a galaxy, and so you can see it's quite bright here. So it looks saturated. It's not, but it's just it's brighter than the rest. So I had to adjust the level so you guys could see a little bit more in there. You can see trails from presumably globular clusters, but sometimes we get stars not on purpose. Anyway, so there's like hundreds of spectra in there. And so that's what I'm talking about, like when you have the octopus going, like the whole multitasking, multi-object spectrograph. You get all of that in one go. And for this project, it's really interesting because that, from memory, is like a 40-minute on sky experiment, and then we had like a really amazing outcome in terms of having all of that, but being able to measure the motions of the stars around this galaxy, but the impossibly faint plumes of the stars using these planetary nebulae as tracers, and then the globular clusters as tracers. So, I mean, that was a very productive 40 minutes on tech.
So how many papers out of 40 minutes?
One, but also with a,
Well, one paper, 40 minutes.
One
great.
paper, but it was, it's kind of a pilot study to then, you know, that opens the way for something. I mean, that had never been done before, and in fact, people were saying, there's no way you can get spectra for this stuff. Of course, because it's so faint. But you can if you use the tracers, so that was like kind of a proof of concept. So we're hoping to get more, but okay. Okay, so this is just something that I think NG could say a whole lot more than I can about. But what I wanted to point out is that so he's shown a lot of these like optical designs before, so I'm not going to go back over this. But in here, which is the focal plane of the telescope, you insert a slit mask, or you've got your fibers there staring at where your galaxies are supposed to fall. And so if you don't get that right, you're not going to get any light through your slits or your fiber. Okay, so that's very important. These things are like mechanically put in. And sometimes, I mean, when I was at DLT, we would put a mask in and there would be nothing through, and there was like 4 channels. And so, you know, the first 2 or 3 would have something and the other 4th wouldn't have. That's because the mask hadn't come in properly, and they were sort of bendable masks. So you have to kind of know what you're dealing with, like before you say apply for time, and then sort of expect these possible losses if you want. But the DEIMOS is actually a sort of a more rigid kind of mask, and so that one is less likely. So if it's misaligned, you can always sort of get it out and put it back in, and then usually it'll come in properly if you did your homework right, and then you actually had the positions of your stars properly set. It should be fine. These are just like little things to think about. Like the mask themselves are not always made, you know, of rigid material. They can be paper, so you might lose some data through that. So I was telling you before about like software to prepare those slit masks, and then, you know, some of them are pretty. So this is for GMOS. Some of them are pretty obvious or easy to see whether you have overlapping slits because they draw them up for you. In here, this is for DEIMOS. It's not as obvious, but the software should do it for you. So if you're, and I think this is the same software for LRIS or something similar to that. But if you've added there by hand, like I said, you can go by hand and then select certain objects. And if you do it in the wrong order, and you grow your slits later, you can have overlapping slits. Okay, so you absolutely have to go back in and then have a look, say, take your ruler and make sure that things don't overlap. It is like a reduction nightmare if you have overlapping slits. Okay, so here's an example of, this is DMOS again, so just slits being milled, very, very precise. And so once the output of those software I was showing you, it goes to the telescope, and then they will prepare the masks for you. This is sort of the mask milling station, and this is an example of how the mask is cut. So this is Lee again and myself as a PhD student, young and eager, holding very proudly our masks for DMOS. Okay, and then now, so I've talked a lot about multi-object spectroscopy using slits, okay, which is kind of more intuitive now that we've heard. Maybe it's not. For me, it's more intuitive to have a slit when you do spectroscopy, okay? But now let's talk about fiber-fed spectrograph, okay? They have lots of advantages. I'm going to go later towards the pros and cons. This is AA omega at the AAT. It's actually like in a room that you can walk in. Who's been to the AAT and seen AA omega? Yeah, Sarah's been there. She's still a student scientist. That's the question was. Anyway, and then you can see, like, it's really nice because if you ever go to the AAT, ask to go in and see at least AA omega. Because it's really nice. It's all open. You can see things like, you know, the filter is changed like that. The grating is changed like that. It's these massive, like, sort of like square pieces that are movable. I mean, I'm not saying you will change it. I'm just saying you can see them. And then someone replaced one of the filters when I was there. It was really, really interesting to see that. This is one of the rare instruments where everything has its guts open, so you can see what's going on. It's really nice. And so basically, lights from fibers are taken into that, so that's underneath the telescope. So it's taken through, and these are like a long snake here, and these are all the fibers that then go to the telescope on this plate here. And so I don't know if you can see, I'm going to show like a video of this in a minute, but these little dots on there, these are sort of the ends of the fibers. And so these are sort of positioned there, exactly where your galaxy or your stars are going to be. Okay. Pros and cons, I think, anyway, I love slits. I love slit masks. Pros, it's got a good throughput. You don't need to worry about, say, what the fiber is like losing in terms of lights through the fibers, although the fibers are getting a lot better, okay, in terms of throughput these days. And then you can do local sky subtraction, whereas if you have fibers, you have to get a special fiber somewhere else, which might have a different throughput, which you have to correct for and everything, and then do non-local sky subtraction, which if you have a massive galaxy in the background is going to be very difficult to get right. So you would want to have, say for this case, if you're using fibers, you might want to have two fibers nearby, one for the sky and one for the object, if you have something over a galaxy. So that's kind of it depends what you're doing, right? Cons of the slit mask, mask preparation is a bit of a nightmare. Like I was telling you, there's a lot of like hoops you can fall through. Masks come in and out, they're not always aligned. And then, yeah, this is getting a lot better, and I'm really excited to show you some videos later, but they can be really, really slow to configure, and I don't really like snakes, so the fiber snake kind of scares me. I told you it's a very narcissistic talk. Okay, so this is what I was telling you. So this is AA omega and how long it takes for it to configure a field. And just think about, like, say your science is you're looking at bright stars in the galaxy, and then you want to configure a field, say, every 2 or 3 minutes. It would be impossible with this instrument. So let's just put one fiber in. These are just the ends of the fibers. And this is sped up. I don't know if you've noticed it speeding up. This is artificially sped up so that we're not here all day watching it. Woo! Even faster. So I don't know if you saw, it's got two plates, one on each end, and so it tumbles. So you configure one plate while you observe the other. But obviously it takes a while, like it'll take, how long does it take these days? Like 20, 30 minutes? 40 minutes. Okay, I will multiply a factor of 2. Okay, so 40 minutes. So you want to have your observations, you want to be observing something that takes at least 40 minutes on the other plate while you configure that one. Okay, just a couple of things. Little warnings I've already said a little bit, but just little bits of advice for you. If you intend to do multi-object spectroscopy, things not to do. Do not do this, okay? I know you're not supposed to do negatives, but that's kind of the point. I want you to pay attention. Do not procrastinate. Okay, don't leave it to the last minute. If it's masks, it takes a while, it takes preparation. You have to select your object. You have to have priorities, so you select the objects that will give you the highest return for your science, especially if you're using like large telescopes. It actually costs a lot of money for us to get time on these telescopes. You have to be prepared so that you make the most of them. Okay, so do not procrastinate. Look at this. As soon as you find out that you get the time, start preparing already. Do not get greedy. Okay, do not try and pack more. This is especially true for slits, multiple slit spectroscopy. Do not try and put more slits by like making the gap between the slits as tiny as it can and making the slits as short as you can so you get the minimal sky on either side and suddenly your seeing is worse, so you've got no sky, or suddenly the cutting wasn't perfect and so now you've got overlapping slits, things not reduced, the pipeline crashes, now you have to go in with your hands and fix the pipeline. Don't get greedy, okay? You'll be happy later if you have 2 or 3 fewer slits, just so you've got extra space and extra real estate, just because it'll make the time you are going to waste trying to reduce the data that wasn't optimally prepared is just not worth it. Okay, and do not be complacent. So once again, once you're observing, and this is something that Kathleen said yesterday, I think, when you're observing, look at each frame. Once you're observing and you're looking at your calibrations, are they saturated? Is your flat saturated? A saturated flat is useless. Okay, so you have to have a look at that. Adjust the exposure times if you need. Do you have arc lines all the way throughout your wavelength range? So that you don't have to go back 2 months later, and depending on the instrument, this could be fatal. Because instruments change, things move, parts move inside instruments, the instruments might have been opened up, and so things are completely different, and there's no way for you to get an arc lamp 2-3 months later, depending on where you're at. So don't procrastinate. Take a look at your data as it comes in, and also the calibrations as soon as you can. Anything else I missed? People who do multi-object spectroscopy? No? So I've got a cautionary tale of greed. This is us, so this is the paper that I was telling you. There's no gap between the slits. And so now if you look, all these like skylines, and this is an arc, I believe. And so all these arc lines are moving across between the different slits. It was a nightmare identifying arc lines in there because the pattern would just fall over. So we had to go in and change it, and it's a nightmare, okay? Whereas if we just had 1 pixel between each, this would have all gone away. Don't get greedy. Okay, so just to look to the future, and I think Andy talked a bit about that. I've got a few videos. So this is an example of AAO, which is a so it's a fiber positioner, and it works. It's got these little spines there, so a bit like an echidna, which I think was the prototype for this.
Well, echidna was at Subaru for 7 years doing science, but ASOP is based on the same technology. Echidna was 400 fibers. This will be 2,500.
2,500.
It'll be much bigger. That's echidna at Subaru.
Oh, that is a echidna.
That's echidna. That's only 400.
Well, I got that wrong. Okay.
But it's a technology.
YouTube video fooled me.
ASOP will look exactly like that, only much, much bigger.
Okay, let's take a look. So these are all like the fiber chips, and then there's going to be a current sent through. This is how long it takes to configure the field. It's done.
Done in X.
Oh, okay.
Done in Y.
X and Y. A good thing you're there, because I'm like watching this. Oh, this is great. That's the configuration. Okay. Next. So it's done. Okay. So when I was telling you before, 40 minutes, you can't do your bright star science and that. You will be able to do this soon. Okay. Here are some of the star bugs that Andy was talking about. So this is a very early video. I think it's we're still like prototypes. So configuring the field. There they are crawling around. They're just walking around.
This is a minimum sort of size that you can actually spacing.
Correct. So for crowded fields, yeah, you have to think about crowding. But hey, this is fast. This is great.
You know, but the echidna, they can get right up next to about a fiber band.
Because I guess they don't have that.
Second.
They don't have the bug.
They don't have the bug. It's almost I mean, it's a fiber and a ferrule, but it's basically almost a bare fiber.
But then the range isn't the same, right?
So there are trade-offs.
They can't go everywhere.
Removing fibers, they have a very defined control radius that they can move. But it's not about the principle to move anywhere.
That's right.
Although in practice, we're not actually doing that. They do have their own limited regions, so they don't have running into each other.
Ah, yeah, fair enough. Otherwise, yeah, the computing, the software for this would be, they all have to know where everyone is. Oh. Okay, and this is a treat.
Are we naming the Starbucks?
This is starbugging.
No, is that one named Barbara?
I don't know. I don't know.
I'm just going to lie and say yes.
Yes, his name is Barbara.
It actually says blah, blah, blah,
That's right. Okay, you guys all know about the future telescopes coming up. I was going through the web and I was looking for which ones would have multi-object spectroscopy capacity, and it's very disappointed to find out that the EELT doesn't appear to have one. Am I wrong? It's bizarre. It doesn't have one in a field. It's got, yeah, IFU's plenty, but so yay, Australia.
That's why GMT is
Correct.
going to be superior instrument.
So yay, Australia, we grabbed the right project. So I'll just you can read it as well as I can. You can go through the web as well. This is just to tell you that of the 3 that are planned and look like they're going to happen, 2 of them will have multi-object spectroscopy.
I will add one thing though. ITSO is planning to build a 10 to 12 meter telescope that's dedicated for wide field multi-object spectroscopy, 5,000 fibers.
That's great. The follow-ups on
LSST.
That makes sense.
But it's all talk right now.
And I'll just give you a teaser for Sarah's talk, where she's going to be combining imaging and multi-object spectroscopy, if you want to. Like imaging and spectroscopy all in one. So stay tuned. Okay, thanks.
Do we have any questions for Curly? Multi-object spectroscopy?
I'll say it's one little thing about fibers versus slit masks. Fibers, you get the same wavelength range versus slit masks, you won't.
That's a good point. You might end up having your H-alpha falling off the side of the chip if you're unlucky.
And I'll say one more thing about fibers. You can have fibers in the same row or the same column on the field. Whereas for multi-object, you're limited to different slits.
Careful not to overlap.
Not to overlap in row space, for example, or for DMOS, so you're in different column space.
Yeah.
Just a question?
Oh, that's something more about.
we know the audience.
You are at the AAT.
Yeah, correct. This is fiber.
Home of fibers. Yeah, I mean, as Amy says, they use the real estate most efficiently compared to slits. But I also note that Exaspec reconfigures in 5 minutes. That's on the MMT in the States. So that's a multi-object spectrograph as well. And it has 2 robots that reconfigure it simultaneously. So it's a factor of 8 faster.
It's a pick and place stuff?
I think so.
So it's just really fast.
It's got 2 robots and it just does it.
How many fibers?
300 over 1 grade. It's probably better technology. I mean, it came on after.
Yeah, those Americans copying the Australians.
It's a Chinese version.
Alright, well, if we don't have any more questions for Caroline, that's it. Thank you very much.